Hello students, I am Dr. Satish Chauhan, your chemistry teacher. In this video 3, we will learn physico-chemical principles in manufacture of sulfuric acid from chapter number 3, manufacture of basic chemicals. Physico-chemical principles in the manufacture of sulfuric acid. The sulfuric acid is manufactured by contact process, and the most difficult step is the conversion of sulfur dioxide to sulfur trioxide. Hence, the physico-chemical principles are mainly discussed with reference to this step. Let us consider this reaction. Twice SO2 plus O2, that gives rise to the twice SO3 plus 196 kilojoules of energy. That means 2 volumes of SO2 gas react with 1 volume of oxygen, produce 2 volumes of SO3 gas. The reaction is a reversible reaction. So that if we consider the total of reactant volumes, so that is 3 volumes, this is giving rise to the 2 volumes. That means reaction proceeds with decrease in volume. The mass law equation for this equation is Kc is equal to concentration of SO3 square divided by concentration of SO2 square into concentration of O2. The reaction is reversible and the forward reaction is exothermic and proceeds with decrease in volume. That is 3 volumes, these are giving rise to the 2 volume. When sulfur trioxide is formed, hence according to the Le-Chatelier's principle, low temperature and high pressure and increased concentration of SO2 or O2 should favor the formation of sulfur trioxide. The rate of reaction is slow at the low temperature, hence the optimum temperature is kept. A catalyst is used to increase the rate of reaction. Effect of temperature. The oxidation of SO2 to SO3 is an exothermic process. Experimentally, it is found that the rise in temperature decreases the conversion of SO2 to SO3. Let us consider this table, which shows the temperature and percentage of SO3 at 200 atmospheric pressure. When temperature is 433, the conversion of SO2 to SO3 is 99%, and when the temperature is 645 degrees Celsius, then conversion is 69%. It is observed that the yield of SO3 decreases at the higher temperature. At 400 degrees Celsius, the conversion of SO2 to SO3 is nearly 100%. But the rate of attainment of this equilibrium is very slow. Thus, the rate of reaction at 500 degrees Celsius is 40 times as fast as that at 400 degrees Celsius. From the above table, it is clear that the conversion of SO3 is more at lower temperature, but at lower temperature the rate of reaction is very slow. At 550 degrees Celsius, it is the fastest, but we have seen that the increase of temperature decreases the yield of SO3. Thus, there is conflict between the favorable equilibrium conversion at the low temperature and the favorable rate at higher temperature. The reverse reaction does not take place appreciably below 550 degrees Celsius. Hence, the conversion is carried out in the 2 stages. Above 80%, the conversion is carried out in the first stage, and 99% conversion is carried out in the second stage. In the first stage, that is temperature is maintained at 595 degrees Celsius, and in the second stage the temperature is kept at 450 degrees Celsius. Thus, oxidation process is 450 degrees Celsius to 550 degrees Celsius. Nearly 100% conversion of SO2 to SO3 is achieved. The optimum temperature range for the oxidation process is 450 degrees Celsius to 550 degrees Celsius. Effect of pressure. The formation of sulfur trioxide, that is SO3, takes place with decrease in volume. We have seen that twice SO2 plus O2, that gives twice SO3. That means 3 volumes of the reactant gives 2 volumes of product. According to Le-Chatelier's principle, increase in the pressure should give more yield of SO3, but SO3 is strongly adsorbed on the surface of the catalyst. In the place where the layer of adsorbed SO3 interferes between the diffusion of the gases SO2 and O2 and prevents the contact of these gases with the surface of catalyst. Increase in pressure increases the thickness of the adsorbed layer of SO3, and hence the gases SO2 and O2 find difficult to come in contact and to react with each other on the surface of catalyst. Due to this reason, high pressure is not employed. The process is carried out at the pressure of 1.5 to 1.7 atmospheres. Effect of concentration. According to Le-Chatelier's principle, an increase in concentration of SO2 in presence to O2 would have more effect on the shift of equilibrium, because concentration of SO2 appears as square term in the equation. To obtain maximum yield of SO3 from the given amount of SO2, oxygen is used in greater proportion. Thus, gaseous mixture which enters the chamber has approximate composition 8%. Composition, that is 8% SO2 and 10% O2, and the rest is N2 gas. Usually, oxygen is mixed with SO2 in the proportion 3:1 by volume. Effect of catalyst. For oxidation of SO2, that is sulfur dioxide, to SO3, that is sulfur trioxide, different catalysts have been tried so that the equilibrium can be reached in the short time. In contact process, platinized asbestos and V2O5, that is vanadium pentoxide, are preferably used as catalysts. Let us consider platinized asbestos. Asbestos coated with finely divided platinum is called as platinized asbestos. This catalyst can be bring about 95 to 96% conversion of SO2 to SO3 at an optimum temperature of 450 degree Celsius. The activity of catalyst is reduced with the use, and life of the catalyst becomes short. About 90% of the original platinum metal can be recovered from the worn out catalyst. Advantages of platinum asbestos: it is very costly, it is difficult to handle, it gets poisoned by the presence of traces of AS2O3, ASH3, Cl2, HCl, HF and compounds of Pb and Sb, because they form a thin film on the surface of the catalyst and deactivate the catalyst. It is essential to purify the reacting gases before they enter into the contact chamber. Vanadium catalyst. V2O5, that is vanadium pentoxide, is the most important catalyst. It is very difficult and gives high conversion efficiency, which is maintained for longer period of time. It has low initial cost and can be easily handled. There is no danger of poisoning. The gases need not to be purified as in the case of platinum catalyst. However, the gases must be free from the dust particles and moisture. Thus, the favorable conditions for the better yield of SO3 are temperature 450 degree Celsius to 550 degree Celsius, pressure 1.5 to 1.7 atmospheres, catalyst platinum asbestos or V2O5, D proportion of SO2 to O2 is 1:3. Comparison between platinum and vanadium catalyst. The initial cost of platinum catalyst is high, but cheaper in the long run. The initial cost of vanadium catalyst is low and also running cost is low. The platinum catalyst gets poisoned by impurities in the gases. No danger of poisoning in case of vanadium catalyst. Platinum catalyst is difficult to handle. Vanadium catalyst is easy to handle. The activity of platinum catalyst decreases. Activity of vanadium catalyst is maintained. Platinum catalyst can be used for higher content of sulfur dioxide, that is 10%. Vanadium catalyst cannot be used more than 7 to 8% of SO2. 90% of the platinum metal can be recovered from the used up platinum catalyst. The worn out catalyst has no value. That means vanadium cannot be recovered from the vanadium catalyst. Important uses of sulfuric acid. Sulfuric acid is extensively used in laboratory and industry. Hydrogen peroxide is obtained by the electrolysis of persulfuric acid, which is obtained by the electrolysis of 50% sulfuric acid. Preparation of explosives such as trinitrotoluene, that is TNT, trinitrophenol, that is picric acid, nitroglycerin, trinitrocellulose requires concentrated H2SO4 and concentrated nitric acid. The intermediate compounds in the preparation of dyes such as nitrobenzene, nitrotoluene and sulfuric acid derivatives of aromatic hydrocarbons are obtained from the concentrated sulfuric acid. It is used as catalyst and dehydrating agent in the esterification reactions. It is used in the manufacture of synthetic fertilizers like superphosphate of lime, triple phosphate and ammonium sulfate.